Hi everyone. After multiple failure of a recording, hopefully this time my theory lecture will be successful and successfully delivered to you. The module that we are going to start with for this class is the theory of database design. So in this database design, then we will look at DB models. In many cases, DB model, database model, is important. In typical computer science database courses, database models are already also discussed, but not much. All the issues have been discussed in the business school when they teach database. Okay, so today's lesson is pretty much like lightweight of database technologies, very similar to business school database models. Only something different from theirs is somewhere here. Let's see if I have. It's not going to be shown. Usually when I Okay, so analysis of the real world, the applications is something that many other disciplines are talking about when they want to deal with the database. So one of the best tools that we can analyze and therefore make sure that our analysis is well understood among the group is the entity relationship models, ER models, so-called. It's called the ER model, entity relationship model. So widely used for analysis. The outcome of this analysis is the conceptual database. Okay, so conceptual database, which is the outcome of ER model, is called ER diagram. So we call that ERD. Okay. And the reason that we do analysis and generating conceptual model, ER diagram, is to build the database in a computer. The way that we analyze, and in the futures, the real world exists, is much more complicated, more complex world than what computer can do. Simply, you can think computer can understand the data in binary, but in real world, the data is not necessarily binary value, but a lot more complicated, right? So there is some gap between database and the model that we have. So there is a gap between here and there. And products, database products that can be running on a computer includes relational database. Relational database has been used in powerful ways for last 3 decades, which is strong and also robust. Okay, but since 20 years ago, after we started relational database, 10 years after we started the relational database, which was around late 1980s and early 1990s, and we need to think, oh, well, the real world, analysis of a real world is more complicated than the features that we can build on computer. So the leading researchers started thinking of constructing software packages, which is database management systems, so-called the DBMS. It's more powerful and functional on computer. It's so natural to think about object orientation. So 10 years after that we have a relational database, we can think of object-oriented database. So we call that OODB. After we have RDB, relational database. Okay, so this is B database, object-oriented database, OODB. We do not have enough time to do these two things deeper, but I can tell you that the strength of a relational database is SQL language. SQL language, why that is a strength? Because it is simple to use. The weakness of a relational database is that there is a big gap between database, computerization and conceptualization of the real world. Big gap between real world situation and the computer. More specifically, in the context of database, we can say that relational database model itself is so simple. But ER model itself is not really relational database model. This is more prone to the real world, which is very much like object-oriented paradigm. Object-oriented paradigm is good for the real world. Relational database is good for the computer. So there is a gap. ER diagram is a good tool, but it's not good tool for relational database. It's a good tool to analyze the complicated object-oriented real world. So without losing any specificity, ER diagram became a good tool to analyze. Okay. So the gap exists anyway between object orientation or ER diagram and relational database, relational database is a little bit advanced from Excel program, if you want to say. Little bit means compared to object orientation, but there is some and big advancement from the Excel, but we can discuss that later. To bridge the gap, we need to have a mapping process. This is a very, very important process, mapping. So what we want to do is from ER diagram to ER diagram will be mapped to relational database. Relational database is nothing but a set of tables. Set of tables. But we don't call it table basis. We call it relational database. Why relational? Tables that we can deal with in relational database is not really a separate table like Excel table. Tables in Excel, they are independent. One table is not necessarily related with the other tables. If you have 10 tables, then they are not really related. But in relational database, each table is a table, but tables are related. If you have a big database, say 100 tables, 100, I would say tables, which means one table has columns and rows, right? So if you have 100 tables, then those 100 tables are related each other. One table represents a small set of real world. Another table represents another. But if you look at the real world, then they are related. So a table is related to another table. So that is a relational database. Okay? Relational database is good, as I said, because it has a SQL language. SQL language is good to relational database. Easy to express. Well, it is easy if you make a simple query, but if you want to make a very, very complicated query in one SQL expression, it's not really simple. It is a real complicated expression also. But anyway, in general, SQL is a simple language. But it has a gap between the database and ER diagram, which is object orientation. If you have another type of database like object-oriented database, then, well, we don't really need the mapping from complicated model to simple models. Both are complicated model. Aha, this is a simple mapping. This is a very, very mechanical mapping. Not the mapping like this. This is all complicated process, which is good, right? Which is good. Good exclamation. So why not using object-oriented database these days? Object-oriented database started in early 1990s and disappeared late 1990s. Why it's disappeared? It is good to represent and good to build a database on computer, but it's very hard to express even simple query language. Very hard to manipulate. Very hard to manage data. Alright? Idea is very good, but reality technology reality is not ready. So from ER diagram to from relational database to object-oriented database, and then this is good for knowledge representation, right? KR, knowledge representation. These days, like the Oracle database, it's a combination of those two. We take the strength from each, which is called object relational database, ORDB. ORDB uses SQL. ORDB also very strong at knowledge representation. Current commercial DBMS supports OR database. For example, Oracle. Okay. ORDB has been on market since early 2000, late 1990s. So it's been about 15 years. Okay. And the other side, this it's not the subject that we will do on this module, but when we install Oracle, and we will practice that. Of course, this course is database security, so along this process, we need to think of security as well. Okay, let's move further. So relational database components has data structures, which is nothing but representation, and the manipulation. So we need to have the language to express what we want from our database. One of the major component of database manipulation is integrity management, which means it gives us a trust. Okay, as I trust the data hour ago, I need to trust. I also need to trust my data 1 hour later, or a year ago and a year later. So always I need to have put my trust on the database. If there is anything wrong, then entire data, whatever the data that I can manage or retrieve from that database is not really trusted, which is a big problem. We lose all database integrity in such case, right? It has been discussed along for the integrity management of database. Okay. To maintain this, database has another big components to design constraints. Constraints is nothing but a rules that we want to enforce, like these rules, so that we want to make sure that rules are satisfied over the course of time, all the time, right? The constraints is one of the language, and then we need to set some audit process or verification process, detection process. All those procedures needs to be developed. So when we purchase the DBMS management system, it has all those components. Simple DBMS does not have. For example, MySQL, it has only data structures and manipulation. Not much about integrity, not much about security. Okay. Security is another big component. But major database management systems like Oracle has all and supports all such features. This is a table. We call that table in general, and in relational database we call it relation. Table in physical context, it has columns and rows. Relation, we have tuples, so one object. This is one object. And then this is different dimension or features. If that is a student table, then student has a student name, student phone number, and student address, and student's major, and so on and so forth, right? And then student has Adam. One of the students is Adam. This is one object, so object 1. For Adam, we have a value for name and value for phone number 111, address, and major, cybersecurity. And on the second object, which is available in the real world, and his name is Charlie, and his phone number and address and major, and more, right? This is what we call relation. Relation, Adam 111 and CSEC, those three values are related and therefore constitute object 1. And another value are related and also constituted to another object. Okay. Not only that, why there is a relation? One table is related to another table. Here, let's say this is a student table, and this is enrollment table. Enrollment of a class, right? And the student name here, CWID. Let's say CWID. This is a course, then course ID, CRN. And then there is a student. It was a student ID. Those two tables are related. The relationship between these two tables represent the real world. The real world scenario expressed that students are enrolled in a class. Alright? So CWID 111 is taking that 111 is enrolled in a course number, say 98. These two different objects. This is object of student. Object 1. This is another object. Object 2. This object is that situation, like some enrollment. An object is not necessarily something that we can see, not necessarily visible, invisible. Still, that object exists. Looking at these two objects, we see the relations. Students is enrolled in a class. Alright, so that story available in the real world is represented in a simple table into those two tables. That is the beauty of a relational database. It has constraints, domain constraints, entity constraints, operational constraints, and referential integrity constraints. A lot of constraints can be defined. Okay, some constraints can be defined as you design, as you create a table. Some constraints may be defined separately. Some constraints can affect only within a table. We call that intra-table constraints. Or some constraints affects over the tables. We call inter-table constraints. Referential integrity constraints is kind of inter-table, interrelation constraints. Simple example of referential integrity is this. Back to our original. What kind of constraints exist? Let's say we have another objects. CRN number is 99, and there is a students 1, 2, 3 enrolled in. The constraints by looking at this table is that this student ID should exist in the student table prior to that enrollment. That is a constraint. Our database does not allow having that enrollment without the existence of that objects in the table of student. Right? Students needs to be created before that student is enrolled in a class. That is very natural. That is very reasonable, right? That kind of things. So a lot of such things are available. So that's what I am talking about. And design, real world design is can be done by entity relationship model. Okay, entity relationship model. The outcome of this analysis is conceptual diagram. I mean ELD, right? This process is called the conceptual model. So this is done, and then you can install relational database systems. For example, Oracle. By the way, Oracle is an OAuth database, but even if you have an OAuth database, you can simply use to the level of a relational database technologies. You don't need to use object orientation paradigm. This is subsumed. Okay. So when I say Oracle, then sometimes simply a relational database, sometimes object relational database. Okay. Let's say relational database system. Then it is table and relationship among tables. This is very simple. Table, as you can see, it has columns and rows, right? Very simple. Only relations. So one cell here is related to another cell in another table. That's it. But in the real world, the scenarios are really complicated, so that we need another process. We call that logical design. Logical design is like this. We have, I'm not going to say much about ER diagram, right? How can we create ER diagram? I'm going to explain this one. Let's say the real world is talking about the custom and order. So custom place an order. There's a situation, and for example, Amazon.com. Then Amazon has a bunch of customers, and then customer can request orders, and orders will be taken care of. So one simple ER diagram is to represent a customer. So real people, right? We have a customer ID and customer name and customer address. Order, then customer can create by clicking some items. Then order is generated. Then there is an order date and order ID, right? One customer can place multiple orders. This is what it says. One customer can generate multiple orders. So order is submitted. So this is entity. This is entity. And submission, that is a relation between customer and order. There's a relationship. Relationship is nothing but submission. Submission is like a verb. Entity is like a subject, right? Or customer submits order. Order is submitted by customer. Entity can be defined over attributes for that entity. Customer has customer ID, customer name, customer address, customer billing information, and so on and so forth. Those all are used to represent the entity customer. Similarly, order, that is an entity, is defined over order ID and order date. Further, the very same entity order, which means therefore same attribute as you have here, right? So these two diagrams can be connected eventually. But order request products, this item, to purchase. Product has unit price and product ID. The same products can be requested by many different order. Many different products can be ordered by many different order ID. So there is a request. Okay, by having those so customer and order, the entity can be nothing but a table, and here order is nothing but a table. So we have two tables, customer and order. One customer can make multiple order, but there is no such case that order is submitted by multiple customers. You can create that situation, but in the current situation, we do not allow that. For example, if an order is submitted, then it should be submitted by one person, one customer, right? In such case, we can make two tables from entity, relationship, and entity models. And this diamond, which relates those two entities, represented by referential constraint only, which means customer ID here should appear customer ID over there. By sharing customer ID, by sharing this customer ID, these two tables are related. Instead of having this diamond, we want to simply share this customer ID into the customer and also into the order. Okay, there's all details of the rules, mapping rules available, but you can simply think why one is good, why the other is not good. For example, customer ID are shared here. Someone may say that why not this guy order ID appears here? So one more column in the table customer so that we have order ID. Instead of sharing customer ID in both, but sharing order ID in both. Why not this? Why this is no good, but this is good? You think the following. One customer can make a multiple order. Then this table, look at this table. This table is like this. So order ID 01, order date, whatever that, customer 111. Customer make another order, the very same customer can make another order ID is order 2. Which is good, right? This in different date. This date 1, this date 2, and date 3. Then the very same customer can submit another order for 3. So this is a very, very simple table. Therefore, we take this. This is good. What about this? In this case, we have only this simple order table, which has 2 columns. However, we have 4 columns for customer. Let's consider that customer. So if you consider that customer here, then we have a customer ID, say 111, and customer name, and whatever that, an address. And we have a common here, order ID. One customer can submit multiple orders. So we have a multiple order 1, and here 111, then order 2, and 111, and order 3. What happens? Because of that order, every time when I create new order, customer name created, address is created. If one customer places an order 100 times, then this, the very same values appears 100 times, which is redundant. Redundant is one of a big problem in relational database, right? To avoid that redundancy, this is much better, right? Only we have order, and different date, and then the same person make that multiple orders. In this case, the very same person, multiple orders. Then we need to create this. If we have more and more, then even worse, right? If we have more columns. What is the problem of a redundancy? Someone may say, oh, if we have a redundant, then storage problem. Yeah, that is the problem. But that is not really the issue. Storage is very cheap in these days. There's more critical problems if we have a redundant data in our database. What happens? If customer change the address, if this the very same customer make 1,000 orders, then that address should be updated, right? If you miss any, then the very same person's information, because that appears multiple times, if they are not identical, then there is a problem. Depending upon which rows are retrieved, you may have different address. That is a problem, right? So this is much better. Okay. So we take this. Someone may also argue that, oh, look at Amazon.com, then you can create address, one or more addresses that all are associated with the customer. You know what? In that case, if it is the case, then you need to split. This customer address should be in another table, so that you simply say customer address ID 1, ADD 2, ADD 3. So the same customer ID customer can register multiple mailing addresses. Then that mailing address itself is a separate table, and that table is connected to this customer table. So if any address details are updated, can be updated at that address table only. It doesn't affect customer table. Customer can be updated solely here on the customer table only. It doesn't affect to the entire long list of address table. Address is a simple table, but it's not really good example, but in another scenario, there may be a big table. Then you need to split those two tables. This whole process is called logical design, which means this ER diagram is mapped to a table relations. It's a logical design. Similarly, if you have this order and products, then this diagram itself still exists. Okay, we have products, we have order line, order and products and order here, and diagram request is nothing but here. This is a request. request diamond in this ER diagram is mapped to its own independent, not really independent, its own table. From entity, relation, and entity ER diagram, we have 3 tables, one each. Here in this case, entity, relation, and entity converted to 2 tables, only tables for entity. And to represent this diamond relationships, we shared the attributes. Attributes of the key of one entity will be shared in another. That's what we said here. But in this case, it's much more straightforward. Order table has 2. Order table has 2 columns, and product has 2 columns. Product has 2 columns. This is not shown here, but assume that there's additional. Request, however, this is a table, so we have a quantity here, right? Quantity there. But if we have only request over one column quantity, then there is a big problem. The problem is that those 3 tables are independent. There is no relations among those. How can we link one table to another table? Therefore, they are connected. The connection among the tables in relational database is possible by sharing a column. By sharing a column. Which one can be shared? The key of each. Order ID here, another key here, product ID here. Right? That's what we say here. By sharing those 2, then they are nicely related. Again, those blue arrows is the indicator of referential integrity. That's what we say here, referential integrity constraints. Okay. Again, what it means is that request can be formed over order ID and product ID. Then this product ID should exist before that request is formed. Of course, if there is no item, then how can we request for purchase, right? That's what it means. If there is no order ID, then how can we request? Order ID should be created by customer, right? There's no. It is almost impossible. Well, it's ridiculous if order is formed where there is no customer. Right? If we think of an object relational database, then by having this ER diagram, it can be converted to object relational database directly. There's no additional mapping process required, like logical design, right? Object relational database can cover nested relations, complex type, but still preserve SQL, complex values and objects, And but object-oriented database and object-relational database, those are not exactly the same. Object-oriented database has its own language. We call that object-OOQL, object-oriented query language. But object-relational database has simply SQL. Okay. Object-relational data model is extended version of relational database. It adopts object orientation, allows attributes of tuples to have complex types. Right? Relational database, which is a table, which is nothing but columns and rows, and the values in each cell should be simple type. We call that atomic type. Atomic type. One value. Which means here, where is my cursor? Here. We don't call that multiple address. We don't call set values like address 1, comma, address 2, and so on and so forth. Okay. Each one should value for a cell should be atomic value. It's not a set value. Non-atomic values. And preserve relational foundations. Declarative access, which is SQL. There's no procedural. In general, declarative means we can access data by expressing what we want only, not necessarily by expressing how we want. How means how we can access a table, how we related one table to another, how we can access real storage, how can we retrieve it, how can we combine them, is there any way that we can optimize it? All such hows are neglected, which is SQL. Therefore, we can say that it's a simple. Upward compatibility is possible, which means the OAuth object relational database comes after relational database. So object relational database can include all the features of a relational database, which is good. Although we install Oracle object relational database engine, but still you can practice pure relational database. Nested relations possible in object orientation. Some of this. If you have a title, title of a book, it's a set value. See, author, we have Smith and John, and the publisher is a set, like a tuple, called a tuple, right? We call this a list in Python. Set of the same type of values is called the list. And for one object, we can represent them over multiple attributes. It's called tuple. In Python, for example, tuple is in parenthesis, simple parenthesis. List is in our Python square bracket. If it is a set value, then in Python it is nothing but dictionary. Those who knows Python language, you don't have to worry about this, okay? But anyway, nested relation is possible in OR diagram. So I'm going to skip this. Okay, SQL. Structured query language. Third standardization was made in 1999. Okay. So how can we create? How can we use SQL? Sorry. First, you can think of the create a table. You can use the word create and table. Any boldface is a reserved word, which means you have to use in order to create. You have to use create table followed by the table name that you want to create. You can say books, students, classes, whatever you want to say here, right? In our implementation, we will not do OL database. We simply do atomic data values, not set up. So don't worry about this, but this. Bar chart is a character, but variable size character. For example, there is a book and author, then author name is a character type, but not all authors have the same size last name, right? Each one has different size of last name. Therefore, we may use a varchar rather than char. And we do not have to worry about this complicated data sets. For those are available in Oracle, but we do not need to use that. And Oracle also allows you to use large objects. So there is a large objects, two types of large objects: zlob and blob. Zlob is character large objects. If you want to create a database, create a table, each object in a table represents a book. So book is like big size of text, right? How can you store that? We can use it in zlob. If we have image, for example, movie, then you may use blob, B for binary large objects. This is also possible in Oracle. So as an example, two tables are created. Create table publisher as open parenthesis name. This is any italic is something that you need to define. In order to create publisher table, you need to use reserved word in bold faces here. Create table as varchar. and book, title, author, array, publication date, publisher, and keyword list. But in this case, one case we use array and another set of, but let's make simple in this class. But if you want to use the full features of Oracle, then you can use this. But I'm not going to say it here. You can learn it from database course. Okay. So there's a creates. I think this is it for the lecture in this module. Okay, so among yourself, if you have questions and topics to discuss, you can create discussion threads so that you can help each other. And at any moment, if you need my help, then you need to email me within Blackboard. Don't use my regular email for this class question. Mechanical question is okay, but technical questions should be requested within Blackboard email. Therefore, for some cases, if my answer is good to know by all of us, then I can do it within Blackboard. And another question is suggestion from me to you. If anyone needs quick attention from me, then you can write email within Blackboard and then remind me by texting. I think I gave you my cell number, but if you do not have, then my cell number is 914-582-3659. Okay, so text me. When you text, you can start with IASP 525 followed by whatever your message is. You can say, please read my email at Blackboard. Then I can go back to Blackboard and read it. And if it is useful to everybody, then I can post it to everybody. Okay? Yeah. So this is my cell number. Any other issue? Well, yeah, you can text me if you have any issue to me. So I'm always available for you. Okay, let's go from here. I'll see you next time. Okay?